All right, good afternoon, everybody. We got 7-4 today, lengths of curves. And, you know, the integral is all about adding up an infinite amount of things that are infinitely small or, going to zero. For example, if you have this curve and you want to estimate the area into the curve, we could make these big rectangles that would, kind of fit the curve somewhat. And if we wanted a more accurate estimation of the area, we would make more rectangles that are smaller, more narrow. And then if we want more accurate, make even more that are smaller. So we end up integrating we end up getting an infinite amount of rectangles that are infinitely small, in theory. And that's kind of what we're going to do today. So if we wanted the distance of a curve, let's just take a portion of it like they have here, we could estimate this distance by drawing this right triangle and saying, well, this is the change in x, this is the change in y, and the length of the hypotenuse will estimate the length of the curve. But if you wanted something a little bit more accurate, maybe you could cut this into two triangles. You could go change in x here, change in y, and use that hypotenuse, and then go from here, go change in x, change in y, and use that hypotenuse. So you could cut it into two triangles. But if you wanted a more accurate, you could cut it into 1 billion triangles, and with extremely tiny hypotenuses. And then you would have a very accurate, maybe to the 100 decimal places, right? I mean, how accurate do you actually need this to be? So that's the concept. Now, the length of one hypotenuse would be the Pythagorean theorem. It'd be the square root of the change in x squared plus the change in y squared, because you have this right triangle. Well, we do a little bit of algebraic gymnastics after that. We multiply by dx squared underneath, which is like multiplying times 1. We'll distribute the one on the bottom, but square root the one here. So this one that'll end up outside of the square root, and the bottom one ends up underneath each of these as the common denominator. Well, then this right here is 1, and then this is the derivative squared. So that becomes 1 derivative squared. Now that's the length of one hypotenuse. Now we're going to say, well, we're going to add up an infinite amount of those in which the hypotenuse just becomes smaller and smaller and smaller. What you end up having is the exact length of the curve. You don't need to know that. You don't need to know the process, but you need to know this for the test. Right there. Square root of 1 plus the derivative squared. That's not the second derivative, by the way. It's the first derivative squared. And if you look at the next box, they have it more in a, derivative squared fashion rather than looking like second derivative. All right, well, we jump right into examples. That's pretty much it. Just now we need to see some examples of this. On example 1, we're going to use our calculator because we don't have a process to find the integral. Not for this one. So if you want to play along, grab your calculators. And we're going to review some free response questions for the test at the end. And when it gets to the test, I'm not going to tell you how to use your calculator. I will now, but not when we hit the test. That's too late. So you might want to play along. All right, anyway, what is the length of the curve y equals sine of x from 0 to 2 pi? We need dy dx. That's cosine of x. And then we need dy dx squared. We need the first derivative, not the second derivative, but the first derivative squared is cosine squared of x. We're going to integrate from 0 to 2 pi of square root of 1 plus cosine squared x dx. And then we just use our calculator to find the answer. Number 9, 0 to 2 pi of square root 1 plus cosine x squared dx. And I mean, we get the value. I don't know if it means a whole lot. 7.640. 7.640. Derivative squared. On the test, I've had students just put in the function. and just do integral of 1 plus sine of x. It's not what it says. That's not the process. It's the Pythagorean theorem coming from those changes in x and y. This one is meant to be done without a calculator. It says find the exact length of the curve. This curve for 0 to 1, let's do dy dx. We have, let's write this, times 3 halves x to the 1 half. Then this cancels, and we get 2 square root of 2 square root of x. Because 4 divided by 2 is 2. And then we need to square that. So let's square this, which is 4 times 2 times x. So 8x is the first derivative squared. And we're going to integrate from 0 to 1 of square root 1 plus 8x dx. Now, like I've mentioned before, I expect you to know how to do these antiderivatives. Let's write this one as 0 to 1, 1 plus 8x to the 1 half dx. Well, because the inside has a power of 1, if we did the chain rule, we would multiply by 8. So that makes it pretty straightforward. If it's anything other than a power of 1, we're kind of in trouble. We'll have to use substitution or antiderivative by parts. But this one, since the inside's linear, well, no problem. To do the derivative, like I said, we multiply by 8. Let's add 1 to the power, 3 halves, but then we'd multiply by 2/3. But keep in mind, if I took the derivative of this, I'd multiply by 8. But there's no 8 out in front, so we better multiply by 1/8. And we're going to go from 0 to 1. So let's clean that up a little bit. 1/12, 1 plus 8x to the 3 halves. Is it 0 to 1? Yeah, it is 0 to 1. Yep, 0 to 1. So if I plug 1 in, we get 1/12, 9 to the 3 halves. Minus, if I plug 0 in, we just get 1/12. All right, now I'm curious. Well, not curious, but I would like you to be able to finish it here without using a calculator. I would not give you a calculator for this problem. So can you finish it out? What's the value? Rhetorical. What'd you think it was, though? I don't think you had it. (13/6)? Yeah, that's right. All right, so we get 13/6. We always take the root first. Do the root first. You have an option. You can either take 9 to the 3rd or the root first. And we're going to do the root. So let's do it like this. 1/12, 3 to the 3rd minus 1/12, 27/12 minus 1/12. That's going to be 26/12. I'm writing every step out. So I get 13/6. There we go. So we review as we go in this class, and you have to be able to simplify these fractional powers. Do the root first, and it's pretty simple. Next one, a fence is built in the shape of a parabola, 49 minus x squared, and has a straight side along the x-axis. What is the perimeter of the fence if each unit represents a foot? And we're going to use I just mentioned we're using a calculator to do this, so I don't have to stand up here and decide if we can do this by hand or not. So we have -7 and 7, and maybe up here at 49. And here's the parabola. And then here's the other side of the fence right there. Along the x-axis, I say there's kind of this straight fencing. But that's a horribly not to scale graph. If we did it to scale, if this distance was 7, then I'd have, pretty much 7 of those coming up. So the fence probably looks more like this. Wouldn't you agree? That's probably what it looks like. So what's this distance up here and that distance down there approximately? What would you say? Throw me a number. What do you think it is about? If this is all the way up to 49. This is not a difficult question. What is it? You think 49 plus 49 is 343? Yeah. Estimation of the length of the fence. Length, not area. We're doing area. We're doing length here, length of the fence. So what do you think? About 100, right? And then there's how much down at the bottom? 14. So what answer are we expecting? About 112, 113, 114, somewhere around there, right? Seem to make sense. So we got the 14, and then we're going to do plus integral from -7 to 7, square root of 1 plus, if we take the derivative, -2x, so we're going to go plus 4x squared, because we have to square the derivative, dx. Now we're expecting an answer of about 114. Seems to be reasonable. Yeah, there we go, finally. 14 plus, math number 9, -7 to 7, square root of 1 plus 4x squared dx. 113.916. 113.916 feet. It's always kind of nice to know what to expect for an answer. That way, if I got an answer of 6,421, I probably did something wrong. But it seems like 114 was a reasonable answer. Now, the width here going up, it's almost straight up and straight down. There's a little bit more there because straight up and straight down, yeah. So it's, yeah, it's a good answer. Exercise 1 through 10, set up an integral for the length of the curve, graph the curve to see what it looks like, use NINT to find the length of the curve. All right, so pretty straightforward. Letter A, set up an integral. So for this one, we need dy dx. That's secant squared of x, and then we're going to square that. So that ends up being secant to the 4th of x. So integral from -pi/3 to 0 of square root of 1 plus secant to the 4th x dx. And in the past, I've had some strange stuff go in for the derivative squared. I've had the function go in. I've had just the derivative in there. I've seen that before. It's derivative squared. It comes from that Pythagorean theorem. Derivative squared there. All right, well, letter B, they want you to graph it. So let's go y equals tangent of x. And we're going from -pi/3 to 0. Window, -pi/3 to 0. That's 1, 0. I don't know, pi divided by 12. It doesn't matter. And just from doing this today, actually I don't remember. I think at -3 to 2 seemed to be, if I remember right. We'll see. We'll adjust if we need to. There we go. -3 is good. Yeah, that's good. So there it is graphed. Letter C says find the actual length. So we're going to quit out of this. We're going to go math number 9 from -pi divided by 3 to 0. And if I put that, I can just do square root of 1 plus secant to the 4th, 1 divided by cosine of x to the 4th. So we don't have a secant button. We have a cosine button. So they're reciprocals. All right, so we got this right there. Enter, and we get a value. So 2.056 or 7. But I'm curious, how close is that? If I look at the graph of this, it almost looks like a triangle. So what if we used a right triangle to get this instead of calculus? So this would be, this distance right here would be pi over 3. This distance right here would be the tangent of negative pi over 3. Right? So what if we do the square root of pi divided by 3 squared plus the tangent of negative pi divided by 3, that's squared. That should be pretty close to that answer. That's 3/100ths off. So the estimation with the triangle is only 3/100ths off of what we would consider the actual length. So then if you start cutting into 2 triangles and 3 triangles and 1,000,000 triangles, that's when you're getting really accurate. 14 I used to assign, but I don't know. It's more of an exercise in algebra. So let's give it a try. We'll just do it here and then you don't have to worry about it in the assignment. Step 1. Well, it says, find the exact length of the curve analytically by antidifferentiation. You will need to simplify the integrand algebraically before finding an antiderivative. In other words, we're going to do this by hand. And it's quite the algebraic gymnastics that we get to go through with this one. The first thing is, let's find the derivative. So I'll help you out. Here's how I would do it. dx dy is equal to, I would make it 1/4 y to the, not the derivative, the function rather. I would consider it 1/4 y to the 4th plus 8y squared to the negative 1. All right, can you find the derivative of that? Would it be y to the 3rd? This would be negative 8y squared to the negative 2, but then times 16y. Derivative of the inside, don't forget chain rule. This is negative 16y over 64 y to the 4th. That's equal to minus 1 over 4 y to the 4th, right? 4 times 16. Oh, excuse me, not y to the 4th, but y to the 3rd. Y to the 3rd. 1 over 16 y to the 3rd. Now what do we have to do? What did I mess up? Oh, not 16. 4. I'll get it eventually. Eventually I'll have it all right. There we go. Here we go. Here we go. Ready? Ta-da! I got it. Now what do we got to do to this? Square it. Square, and how about instead of squaring, we write it like this? You know, that's what we're going to do. Can you FOIL that? See, I get y to the sixth, that's first. Outside, the y to the thirds cancel, so minus 1/4. Inside, the y's cancel, so minus 1/4. And last is plus 1 over 16 y to the sixth. But we know what that's negative 2/4, that's negative 1/2. So we're going to go y to the sixth minus 1/2 plus 1 over 16 y to the sixth. So we have the derivative squared now. The length is the integral from 1 to 2 square root of 1 plus y to the sixth minus 1/2 plus 1 over 16 y to the sixth dy. And they tell us that this right there underneath the radical is a perfect square. Well, 1 minus 1/2 is 1/2, so I'll give you that. But let's put that in the middle. Now remember, we're supposed to be able to do this entire thing by hand. And the powers under the radical certainly aren't to the power of 1. So we're going to have to get rid of the radical. That's the whole objective here. Once we can do that, we're good to go. So what does that factor into? Talk about an exercise in factoring. And they give you the hint. That's the hint. Maybe not the greatest hint ever, but that's the hint. So what goes in there? Y to the third plus just 1/4. How are we going to get that? So you're close, right? You're real close. 4y to the third. There we go. Now, when we FOIL it, the y to the thirds would cancel out and we get 1/4 plus 1/4. That's where you'd get the 1/2. And now we're home free. Now we're good. Because now we have integral from 1 to 2 of, not equals, of y to the third plus, how about we make it 4y to the third to the negative 1 dy. Because the square and the square root, they'll undo each other. Is that what I want to do? Oh, no, I don't want the 4 in there. I want it like this. How about we make it 1/4 y to the negative 3? How about we make it like that? So this is 1/4 y to the fourth. This would be 1/4 y to the negative 2, but times negative 1/2. So that ends up being minus 1/8 y squared from 1 to 2. So 16 divided by 4 is, 16 by 4 is 4. Minus 1 over 32. Minus, plug 1 in, 1/4 minus 1/8. So 128 minus 1 minus 8 minus plus 4, all over 32. 127, 119, 123. 123 over 32 is the length of the curve. I don't know, I always thought that was kind of a fun little exercise in algebra. See if you remember how to FOIL and how to manipulate all this. I like that one. That is lengths of curves. So you have to know where to go. First page, down here. Well, actually right there. Integral of square root of 1 plus dy dx squared, or dx dy if it says x equals. So if the equation says x equals, you don't really change how you do it. You just do derivative of x with respect to y. instead of derivative y with respect to x. All right, I thought, I didn't think this section would take much, so it gives an opportunity to review for the test. Here's where you might want to grab your calculators for sure and practice this stuff. If you just take some time, well, let's read the problem. Fish enter a lake at a rate of this. So here's enter. And then fish leave the lake at a rate of this one right here. So this is leaving. E of t and L of t are measured in fish per hour, and t is measured in hours since midnight. I think it always saves a little bit of time to spend a little time typing this into y1 and y2. This is what I would do. 15 sine of pi t divided by 6. Yep, 20 plus 15, I got it. And then 4 plus 2 raised to the 0.1 x squared. Usually doesn't take very long, and if you use them again, you can just use y1 and y2 now. A, how many fish enter the lake over the 5-hour period from midnight to 5 a.m.? Give your answer to the nearest whole number. So that's going to be the integral from 0 to 5 of enter. How many enter? So E of t. E of t is the rate. So if we integrate, that'll be how many. So now if you go to the home screen, we can go math number 9, 0 to 5 of y1. Variables, y variables, y1. So you go to variables, y1 with respect to x, and you don't have to type in that formula again. You could if you wanted to. And it says to the nearest whole number, 153 fish. What is the average number of fish that leave the lake per hour? So what is the average rate over the 5-hour period from midnight to 5? Well, it says not the average number of fish, but it says but you have this per hour. So that suggests not the number, but per hour. That's the rate. And to find the average value of a function, what are we doing? Leaving? That leave, we're going to take 1 over 5 minus 0, integral from 0 to 5 of L of t dt. That's how you find the average number of a continuous function. So math number 9, 0 to 5 of y2, variables, y2 dx, and then we'll divide that by, not 6, 5. 6.059. 6.059 fish per hour on average is, so about 6 fish per hour are leaving. At what time for 0 to 8 is the greatest number of fish in the lake? Justify your answer. So for letter C, we'll have time and amount. And we're certainly going to pick the endpoints. So not 0, but we'll make that an 8. Maximums and minimums can happen at the endpoints. And then in the middle, we want to set the derivative equal to 0. That's how you find maximums and minimums. You take the derivative, you set it equal to 0. Then, a little more than that, you decide when it switches to positive and negative, but instead of doing that the old way, we're going to actually find the amount and compare those amounts. Well, we have the equations in y1 and y2, but let's fix the window. First of all, let's make it 0 to 8 so that we don't have any other intersection points that could distract us. So 0 to 8. And we would go by ones. First hour, when I did this the first time, I had to play around with the numbers a little bit. I did 0 to 300. That was way too much. 0 to about 60 seems, if I remember right, seems very reasonable. When we graph that, 0 to 300 was way too big of a window. But I just kind of guessed at first. There's only one intersection value, so there's only one critical point. That's where they intersect. So we're going to calculate the intersection point. Enter, enter, enter. The other value we need to use is 6.2035. Keep on going. All right, now the amount that's in the lake would be the integral from 0 to 0 of entering minus leaving. But for the sake of this problem, that's 0. Integrate from 0 to 0. So the next one is integral from 0 to 6.2035 e of t minus L of t dt. And if they told me an initial value, I missed it. I don't think they did. No, I don't see an initial value. So we assume that the lake is empty. All right, well, if you look at x, if you type x now, if you did the intersection, x holds that value still. We can do math number 9. We can go 0 to x because it's holding that value. And then y1 minus y2. So 135. There's 135.0149, keep on going, fish in the lake then. And now we need 8. So all I got to do is come up here, press enter, change that x to an 8. 80. So integral from 0 to 8 of e of t minus L of t dt is equal to 80.9199. Keep on going. At what time is the greatest number of fish in the lake? The greatest number of fish in the lake happens at t equals 6.203 hours. D is the rate of change in the number of fish in the lake increasing or decreasing at 5 a.m. Explain your reasoning. Students have not liked this one all day. They debated me a little bit, not too much. I can usually convince you fairly quickly. How do we decide if a function is increasing or decreasing? Forget that problem for a second. How do we decide that? Yeah, if the derivative is positive or negative. So how are we going to find out if the rate is increasing or decreasing? It's the second derivative, isn't it? It's the derivative of the derivative. Make sense? That's how we decide if the rate is increasing or decreasing. We're talking about acceleration, really. Now, the functions that we're given, I consider the first derivative. I consider the original function how many fish. I consider this the first derivative. So to find out whether the rate is increasing or decreasing at 5, we take entering prime of 5 minus leaving prime of 5. And a couple students, and I get it, I totally get it. This is like the knee-jerk reaction. Wait, how come you're taking the derivative? Don't we already have the derivative? Well, yeah, we're seeing if the derivative is increasing. So we actually have to take the derivative of the derivative. So math number 8 does derivative at a point. So with respect to x, I have the equation in y1. So y1. We're evaluating at 5, so that is actually the entering. And then we'll minus the derivative, math number 8. X, I need y2 there. Variables, y2, evaluated at 5. So there's entering at 5, derivative, minus leaving at 5, derivative. And the overall rate of the fish, so the rate is actually decreasing. So negative 10.7227, let's say. And it says, explain your reasoning. Here it is. That's less than 0. So decreasing. Explaining doesn't mean write a whole paragraph. Sometimes it's just a couple symbols. Less than 0. The rate's less than 0. The derivative's less than 0. There we go.